There's a circle around the image today. If you look.
I think they'll figure it out. And when you send emails to everybody,
The email is sent. Should I say something about the circle?
Say something about the circle.
Oh. Okay.
And our esteemed speaker can say something about the speaker.
No.
Introduce yourself and mic cues.
Yes. We are live.
Make sure the mic is on.
It's a three-position switch, so talk.
That's plausible. Let's go with it.
All right. You're the guy. Somebody messed up the goalkeeper of the Russian football team with a green label. You're the green label. You're the people who did that in Saturday?
Wait till soccer comes to open. Competitions for worst soccer hooligans in the world. Tell my kids, it's not a contest. Whoa. So, say who you are and start talking.
Good morning, everybody. I am James Bowman. I'm here to talk about a C running on the GA144, which I will demonstrate something. Now, I don't have a lot of C running on GA144, so I don't expect it to be running Zork or anything, but I do have Hello World there. So, just setting expectations that it's a big job getting C running. First question is, why? Is it possible? How do you do it? All these are kind of open questions. It sure would be nice if you could get the GA144 and run regular 16-bit C code on it. It's become quite popular over the years. If you don't run C on your GA144, then your choices are writing native colorful code or using polyform. Polyform is okay, but obviously a lot of embedded work involves C. So it's rather nice to have a C processor on the GA144 running the show with and not consuming all of the chip's resources. The GA144 has 100 nodes, so it'd be nice to run C on a few of them, have the rest running dedicated, optimized hardware things. Next point is nobody's actually got C running on the GA1, not even close. So it's all very well waving your hand and saying, yeah, just get the pilot going and they can execute code. Nobody really knows how to do it, and it's a big job, and so you're kind of adrift. You don't know how to make it work. I mean, we do know that the solution probably involves a virtual machine of some kind, and that virtual machine is going to be what GCC targets, and that's going to execute the code. But that wouldn't even fit on the back of an envelope as a design. So it's really wide open. So first problem really is just where to start. How do you do it? Well, here's a big clue that if the C runs on this chip, which is a low-power chip, then it should be a low-power C. No point in saying, here's your low-power chip. And by the way, if you want to run C on it, get an extra battery because it's a power-hungry implementation. So it needs to be a C that is power efficient. And we can start with that and say, what do we know about power? Well, famous number that the Green Arrays people talk about is the energy required to execute one instruction, 7 picojoules. That's not a lot of energy. If, on the other hand, you access memory, the outside external RAM, which is where your program data lives on a CPU, that's a lot. That's a factor of what, So,
I like that.
so do that, and don't do that. This is the code design. How do we avoid RAM accesses? Well, the C program is going to access RAM. We can't do a whole lot about that. But the C program, most RAM accesses are actually instruction accesses. Obviously, every instruction that we execute in a virtual machine is going to go to RAM. And we can reduce those by increasing code density. This is obviously this is too small to see. This is a paper from 2009, very interesting, where they actually did the legwork and compiled a bunch of small inner loops on various CPUs. And it's a lot of work getting all of these things running. They've got all of the, it's color-coded. You've got the BLIWs in red, obviously this is disaster, the codes density like titanium, you remember that. And then all the risks are all in green, and they put the embedded targeting CPUs in blue. The smaller is better, this is code size. And they put tiny CPUs like the Z80 and 6502, they got the CPU running on those. And those are in purple. So this is like, the oldest CPU here is from the 60s, and obviously the very latest ones are on there as well, things like ARM and DOM mode. So we've got a lot of coverage here, and what was immediately striking to me was this winner, this overall code size here. And this guy in purple, we haven't miscoded it to make it CPU, but it's actually the PDP-11. PDP-11 is from the 1960s. Came out in '69, which is if you do the math, that's 45 years ago, so it's old. PDP-11 beat all the others on overall code size, and it did okay on some of these other benchmarks. This is like string comparison. PDP-11 does it in like 8 bytes or something, so it holds its own against all these others. And there are other winners on code size. Obviously, x86 is quite famous for having compact code. So it does get beaten out in other categories, but often architectures get good code size because they're really complicated. Like writing a virtual machine for x86 is not appealing because it's this huge, complicated thing to decode x86 on things. So you kind of want an execution model which is as simple as possible while getting good code size. Looking through this list and going through all of them, it ended up that the PDP-11 was looking pretty appealing. Run through a quick refresher, just in case anybody hasn't written any PDP-11 assembly code lately. What a great machine. So PDP-11 came in various models. First was the PDP-10, which left out a lot of luxuries like an excuse of all instruction. That was extra. So extra for it. Yeah. So it doesn't come with the base model. So, this is the PDP-11-10. It's particularly interesting. So this is that was 1969. Very unsurprising machine because these guys were building without a big wire RAM and early ICs. So they aim low. So what we've got is 8 16-bit registers, and out of those, the stack pointer is always register 6, and program counter is register 7. So the program counter is just another register. This is super important. That kind of idea is very much gone out of fashion with the stack pointer and program counter are kind of special. Instructions are always 16 bits. This is good for decode, as simple as it gets. And yet, it still gets good code density, which is kind of surprising. So even with fixed size 16-bit instructions, you say, well, every instruction is going to be 16 bits. They're going to lose out to x86, which has bytes as variable length instructions. But we actually managed to get decent code density with this quite, I wouldn't say crude, elegant design. So this particular class of instruction here, which is the two address instruction, which is the important one, things like move, and you've got a 4-bit opcode which tells it what to do, whether it's a move or an add or a Quick catch up, guys. PDP-11. And here's the source where the opcode takes its source from, and that's the destination, which is a read, modify, write system. And then so each source addresses a 6-bit field. And then this is what the 6-bit field looks like. It's got a 3-bit register, which picks one of those 8 registers. It's got an addressing mode field up here, and then which is controlled by this, which you can have register direct, register. The register holds a memory address, and then the register gets incremented afterwards. Register gets pre-decremented before accessing memory, and register plus an offset. The offset follows the instruction with the instruction stream. And then this is kind of cute. It's an extra indirect flag. So it does all of these things, and then if this bit, if bit 3 is 1, then it does an extra indirection. And this gives you, obviously you have all 8 registers are accessible, and then you have 8 effective addressing modes. You have these 4 with the indirect off and on. So you can synthesize a lot with this. It's really kind of quite fancy things. So if you're doing register with post increment, it goes to the register, uses that to access memory, increments the register, and then does an extra indirection on memory to use that as a pointer. So it's kind of fancy. If you're willing to write PDP assembly code, you can pack a lot into one instruction. Particularly as what you don't really get with modern architecture. It's a memory-to-memory architecture. So you can move something out of memory, add it to something else in memory, all in one instruction without even touching register. These 2 things can refer to memory addressing. Some things that are not obvious are how does it do, are ways of combining these addressing modes to achieve things that we think of as built-ins in the modern CPU. It doesn't have anything like push or pop. Instead, all you do is you move R0 to the stack pointer with pre-decrement. That has the effect of push. So the assembler mnemonics it supports push and pop, but this is actually the code that is generated. Same with pop, you move from the stack pointer with post increment to R0. So one thing that is a bit of a wrinkle here is that the increment operator increments by 2 if you're accessing word. So if you're wondering where C's increment and decrement operators and all those things came from, it's this. C language was heavily inspired by the PDP-11 assembly. Kind of hoping that the C compiler is going to be able to map those C language structures into addressing modes on the PDP-11. Clever stuff. They don't have any support for immediates. And I went through the source and destination. How do you add an integer to another number? Well, here's how you do it. You specify an addressing mode that keys a program counter with post increment. So here's the instruction. And then immediately after the instruction, you put the constant that you want to use. So CPU fetches this instruction, and then the program counter is pointing down here, and then for the source for this particular field, it fetches 1, 2, 3 out of the program stream, increments the program counter because it's post increment, so it's safely pointing at the next instruction, and there you go. You've got exactly the same effect as moving an immediate into that account. So there's no actual direct support for immediates, you just use these addressing modes with the register. Another unexpected thing you can do, this is moving from the top of the stack into the program counter, which is a return. So there's no actual need for a return instruction. As a comes, the machine does have a return instruction, but I think that's the assembly. So this is nice. So by implementing just this core of addressing modes and 2 address instructions, you get an awful lot for free. And then this reduces the amount of ifs and buts that you have to handle in your virtual machine, which is a big space saver. Okay, so inspired by the exciting possibilities of the PDP-11, I coded up that 6-bit field decode. So those 6-bit fields that form the heart of the PDP-11. I coded them up in assembly code for the F-18, and it can use 27 instruction words out of the available 64. So this is promising. So it's kind of got the heart of the PDP-11 in there as a single function which reads 6 bits and then delivers an effective address. And that's only used half of the available code. So there's going to be room for something else in that code. Okay, so how is it actually going to run code? So I took a bit of a shortcut. I'm not running out of real RAM for now. I'm using a node on the side as a small RAM of 64 words. And it was a big simplification to not put the registers anywhere in the actual node itself. So the node is full of code. There's no place to put the registers. So I put them in RAM location 0 through 7. So as an implementation, it's one of those sucky ones. It uses the beginning of memory to keep its registers. So every time you access a memory, it's actually a RAM access. Okay, so how are we going to execute instructions? Well, obviously, when you're executing something like this, you have to compute this source, its source destination. So you have to compute this source, read from RAM, compute this source, read from RAM, do the actual map, which in this case is an addition, and then write the result back into this address. So you've got to read, write, read the actual instruction and then write. And that's the general pattern for all of these binary instructions, binary operators. We normally would have RAM access operators in a traditional form style like this. We have a RAM fetch which takes an address and returns its value. That's good. And then a RAM write, which we give it a value and address and it writes into RAM. But the big problem with doing this is that as you're operating, you need to keep this address around on the stack somewhere, and it gets a bit tricky, particularly on the F-18A, which doesn't have swap. So you kind of want to avoid stack juggling as much as possible, just get the stack lined up so things are in the right place. So instead of this, you take the observation that it always does a read, operate, write. But this read, this second read from the destination, is always to the same address that we're writing to. This is reading SP plus 20, and then we're going to write to SP plus 20. So what if we have operators like that? We're going to have a RAM read, which takes an address, but the RAM write just always writes to the address that we last read. So we do a read to do the first operand using RAMAC, we do a read to do the second operand to do RAMAC, and then we just always write over the second operand. This works great with this particular PDP-11 style to-address instruction. So we do RAMAC for the first one, RAMAC for the second one. We do the addition for the instruction, and then finally, RAM write writes to this same address that the last RAMAC fetch. It's a big simplification. Kind of a key to get to the whole thing right. Well, to-address operators happen so often, why not just make a new word called source dest, which just stacks them both. So after source dest is run, we've got source and dest on the stack, we do the addition, and then we do a RAM write. It's sort of a useful factor, and then other words would just differ in that they have a different instruction. Which leads us to where do these instructions live? We've got a real PDP-11 sometime in the mid-70s when it got put on a single chip. And a lot of the time when you look at chips from this era, you'll see these giant blocks kind of look like data. There's lots of a lot of structure, and here are the pads around the outside, and this is obviously some kind of arithmetic. This, I think, is the register file, but what are these guys? They look like just ones and zeros, and in fact, that's what they are. This is the microcode that implements the CPU. So microcoded CPUs have giant ROMs on them, which hold the instruction set, which interprets the original key opcode system and turns them into a series of control pulses at this bit, the actual computer, can execute. So we've got this microcode store, which is, if you like, an inner interpreter for the chip. And so that's the way we lay out the node. So this node, which is the virtual machine, which is where all the action is, doesn't know how to do anything involved in actual instruction, because there isn't any room for it. It's only got 64 words. About half of them are taken up by just computing, handling the 6-bit fields alone. So we've got housekeeping, it's got fetch instructions, it's got to parse the instructions. So there's no room to actually hold the instruction for add, for example. Even that wouldn't fit. So we put all of the instructions in this screen. This is effectively the microcode store for the virtual machine. So this guy gets an opcode and he doesn't know how to map it to instructions. He passes it to 507, which effectively looks it up in a big table, and then turns it into a short sequence of instructions, which it then passes back to 508. 508 executes those instructions, and that's how an add gets executed. Okay, so here is the actual code for add. This is a little fragment that lives on one of those green nodes. So here is the opcode mask for add. We're saying if these particular bits get masked out and they match this bit mask, then this is the 4 instruction sequence to implement an add. So everything is a...
This number, remember that there are awful, right?
Yeah, PDP-11, because of the 3-bit addressing fields, yeah. It really worked well in Octal, and I guess that's why C had that Octal.
Yeah, exactly, early on.
Yeah, yeah. Yeah, so we still have support for Octal, we just start the number with a 0, so it's actually going to get removed. It's really out of fashion. So yeah, I try to use Octal whenever possible, because all the PDP-11 documentation lists the opcode syntax in Octal. So yeah, so this is the Octal mask to pick out an add, and a search running on those green nodes runs through the opcodes trying to find a match, and when it does find a match, then it returns these 4 opcodes. And this is just what I showed earlier. This is how it does an add. It parses the source and destination fields, does the actual addition. Have to put a not there because everything is 4 instructions, and then we end up by writing it into RAM. That's how an add gets executed. Just for fun, here's something similar move. It's actually just the same as a RAM. Obviously, the bit pattern is different. How do we implement a move on an architecture like this? Well, you just drop the destination. So we've got the source and the destination in red. Destination just gets thrown away and we just use the source. The source gets copied with the destination. Okay, so each of those particular patterns is in these nodes. And to begin with, when I was just supporting a couple of instructions, they all fit in node 507. So node 507 has a little search loop, and then I think there's room for about 8 instructions in each node. But soon ran out of space, because obviously the PDP-11 has a lot more than 8 instruction patterns. So then it scales rather nicely. 507 just spits out a query to its 4 neighbors, and they all start searching their tables. They now contain all the tables. So there's actually room for 24 instructions here on the neighbors. And this is something which on the group array scales quite well. You can just keep on extending outwards. So if you wanted to do more instructions, it's easy just to put more nodes around the outside and just distribute the query around those nodes, and then they'd all search in parallel. And then the one who actually matches the instruction, it returns the 4 instructions back to 508. So 507's job is just to send out the query to the 3 neighbors. They all start searching in parallel, and then the one who gets it sends back 4 instructions. 507 just carries those back 4 to 508. And that's not a lot of code on 507. Okay. I should say one more thing. This is just a wire node for the debug interface. This is the VM, as I said, where it all happens. And then this is memory. This node is just completely blank except for 64 words of data. Okay. All right, so there is hello world. So I don't have, and the reason it's using ints to store its characters is because I don't have characters that hard. Talk about why. So what it's doing is it's running through that array, sending input jar sends the character to the debug interface. All right, so I'm using the standard GCC cross compiler built for PDP-11. I tell it I've got a PDP-11.10, so it uses the correct old instructions. There's the loop there at the top, and then this section is trying to disassemble it, but this is actually the hello world text. Okay, and there we go. It's compiled it and downloaded it to the green arrays, and those are the words that came out of the debug interface. There's a little banner that comes out where it sends 55 AA on the interface just as it boots, and then it ran the code, and there we have it, hello world. Something a bit more ambitious. Straightforward stuff. GCC compiles it. This is actually at the limit of what will fit in the available memory. It's coming up to 110 bytes, so with the stack, it's just about fits in the available memory. So then there's the code for it. The PDP GCC port kind of still works, so I was kind of surprised that it's functional. But it does generate code. It doesn't actually generate very good code. It's not that surprising, because who uses GCC to compile PDP-11 code? But it is still functional. It does not support C++, interestingly, that failed. But I guess nobody really wants to run C++ on their PDP-11, so that's the main code I've got. There's one thing in here which is here. This is like our magic instruction. So MFPI is some housekeeping instruction for the old PDP-11, which I've actually just used as my debug instruction. So MFPI is implemented as an instruction which sends a value to the debug port. So that's if you like my printf instruction. Okay, so we're done. So factorial prints out the factorials of the numbers 1 through 9. There we go. There's the banner first, and then the factorials of 1 through 9. So it does work. Function calls work. All the registers seem to be working fine. If you're careful about which instructions you use and don't use bytes and things, you can actually write PDP-11 C code and have it execute. Yeah, so that's what I was demonstrating there. It takes all of the, it loads the, compiles the code, then loads it into node 509 as a big chunk of 128 bytes of memory, and then it just lets the VM run on it and watches the debug interface. So pretty simple stuff. PDP-11 is quite orthogonal, but if you do a byte access, then it's quite complicated which parts of the memory operation actually use bytes, because one given parameter might involve maybe 3 memory accesses of this sort of indirection scheme. And it's only the last one which affects the byte, which is quite easy to detect, which is the last address in an evaluation in hardware. But in our implementation, it's highly factored, so actually figuring out which is the final memory address, the final memory access, to turn that into a byte address, that's quite tricky. So that does not factor very well at all. So bytes, I can't figure out how to fit them into the virtual machine. It doesn't help that F18 doesn't have any byte operations itself. You have to regulate it. So the code to handle bytes on the actual underlying machine involves shifting and masking, so that also is quite common. Fogive 11 is a flag space machine. It has a flags register with an overflow flag, a sign flag. I think emulating flags whenever you're doing any virtual machine is complicated. So I've just taken it out at the moment, sort of kind of keeps track of the 0 flag. So those are not done. And I think those would be too much. So I'm going to say that doing a full PDP 11 would be really tricky, because there just isn't room inside the virtual machine to do all of these subtle operations. But that's kind of a shame. It wasn't really my goal to build a virtual PDP 11. It was more to understand what works and what doesn't when you've got a virtual machine running C. So obviously, particular attention to the things that didn't work out. You've got to have some plan for byte operations. Think carefully about flags. Obviously, you have to have some kind of conditions, but what's the minimum you can get away with? But basically, orthogonality is not only pleasing to us, oh, isn't this an elegant design? When you're actually implementing it on a really tiny virtual machine, then it's kind of a must. You just don't have room to cope with special cases. Instruction decode, that's the whole thing that those green nodes, while they're looking up the instructions, it's kind of a waste. In the end, you have to do some kind of linear search trying to match decode or match instruction patterns against their particular action, in this case, this tiny instruction system. So when you look at high-speed CPU emulators that people use these days, what they do is they decode all possible bytes and then all possible second bytes and then look them up in giant lookup tables. Nobody actually bothers with decode at C because it takes ages to extract the bits. It's all very well in hardware where you can just wire up some random bits and decode instruction patterns. But if you've got a tiny machine that doesn't have the luxury of 256K lookup tables, then think carefully about the decode and lay out the instruction pattern so you don't have to do any decode at all. But basically what I found with the Fogive 11 is that it is actually possible. Not particularly impossible to get a GA144 run in C. Now, there's one caveat there that you might ask, how fast will it run? Obviously, it's not very interesting. If I can take my $10 GA144, run C code really slowly. And that's a bit of a problem at the moment, because I've got about 1 minute out of it. That's not that great. Even the 8-bit microcontrollers get about 8 MIPS. Those are RISC MIPS, and the Fogive 11 is disk, so it's not quite apples to apples. In the Fogive 11 instruction, you can do a lot more work than you can on one of these RISC CPUs. But even so, something clearly needs to be done about the performance of the thing. Otherwise, it's just not that interesting as a CPU. And that isn't just performance, isn't just speed, it's also power. Because of course that node layout was running full time. So if it's running full time and it's getting 1 MIP, then that's 3 milliamps. And that means that we're getting some pretty lousy efficiency. So each instruction is burning a lot of people, like 20,000 or something, way more than actually get to almost any other CPU. So obviously some work needs to be done. EDP11, yeah, was an interesting experiment. And a lot of the things like the importance of read, modify, write, and the orthogonal instruction layout, those were good to find out. But clearly some related avenues to use. Okay, that's all I got.
Good job.
What I've actually been doing is looking at doing a stripped down version of this stuff. So just removing things until it actually does. So it's still possible to have GCC init code for the architecture, but a lot less the bells and whistles of the PDP. And you're right, I mean, there are a lot of other architectures to look at. Right, and that's what I have to do. We're taking, actually, it's a lot easier with GCC if you start with one of their targets and then modify it.
Yeah.
Just doing it from scratch is
Do you have a guesstimation of how much of an improvement in efficiency you'll have by getting rid of the PDP?
Yeah, so I got it running yesterday. I'll show it, it's not ready yet. But it's about the same as an MSP 430.
Ooh.
Which is an actual CPU that you can pay cash money for.
Absolutely. Ooh.
So now I say about it depends on construction mix because they've got slightly different architecture. It's about the same, and it's about the same energy per instruction as well.
Ooh.
So it's not completely useless.
You're at the optimum end of the market, at least.
Yeah. So with this guy, if you've got a memory interface, you can just of course lay out several of them on the GA124. So that obviously doesn't do anything for your energy per instruction. Suddenly got two that are running over time.
But
what it does do, it gives you more available maximum compute.
yeah.
So you could imagine 8 or 10 of them running on a chip if you had such an application for it. Well, ideally, so you've got your application, and you've got your general purpose C processor running in the corner.
Right.
Then all of the application-specific stuff should be put into the rest of the chips.
Right.
So the C processor is doing things like booting, housekeeping, just this general overview. But all of the heavy lifting should be done by application-specific nodes in the rest of it. So in a sense, the C processor's job is just to talk to these dedicated nodes and maybe run something like the TCP/IP stack.
Oh, it is at least. Application specific and very powerful.
That you started made that the last question. Did you end at lunch? Okay, well.
Great
I'm
job.
going to ask you to hold your further questions until lunchtime. And thank John very much.
Absolutely.
Yeah, they put in this idea that all gives you direction. Instead of we all do business, we all have
No, I have some. I have mine.
our application. This is And use this processor. I just come up with a way of doing it that is size or speed efficient. That's the first option.
Now, of course, you've got size.
Okay, everybody wants an opinion?
Next one, yeah, put the next one on. It's picking you up, yes. I hope. Unless it's picking up. Actually, tap that microphone. Tap it. It's not on. What am I missing?
Secure position switch, make sure you have it on the standby. Oh, yeah, I think it's on the top.
And I'm not sure that I'm on.
Okay.
Yeah, go.
Okay. All right. Okay. I'm King. Hello, everybody. I think I've told this group that I've stopped programming. But a couple of weeks ago, I got this board, and on the board it says 4 screw at one. And that and the Taiwanese guy who designed this one, he actually used this board to do a laser recognition. I think it's obviously they are using laser to do PC board. So I saw some pictures of it. And so I asked the guy, what kind of board is it? Well, they keep on back and forth and didn't get much. Obviously, he's using back and forth. And so forth.
SwiftX.
And I tried to get SwiftX and couldn't get anything going. Asked questions, nobody answered.
Where should you ask?
Yeah, where did you ask?
The guy who lay out this board.
Oh,
Oh,
you may not be the best person to ask about SwiftX, right?
right. You need to ask on the
And,
fourth ink list.
it's very interesting in that, this is the STM 32 chip. This chip, this chip is on the left. And the same chip was used by the I have it here, okay? And you can see the one move it, so it's the SPM 32F4, and the discovery put out by SVFIG micro just like this one. This was the SPM 8S, which was released around 30 years ago. I did a port on this one. I'm kind of familiar with it, and so I immediately went to DTT to get the SPM 32F for 1695. So that's really nice.
That's with the discovery board.
Yeah.
Evaluation board.
Yeah, that's right. That's the discovery board with the 3-axis geometry. Yeah, it's very, very, very. So, it's a very nice board. And I downloaded the software package and use the file SDK. And look at this demo. It's just tremendous. So many files just to get this to demonstrate. And I was kind of discouraged. And this one has a serial interface. So ST Micro, they implemented what they call system boot code inside the chip. So that when you boot up, if you set the boot key, if you set the boot 0 to high, then it will jump, when you start, it will jump into the system and run the boot code. And this boot code is interesting in that it's looking at almost all its serial interface, waiting for a particular pattern. And if they got that particular pattern, figure out the ball rate, and start unloading from so this way, and this board, the Taiwanese, they use this and just take, put in another USB chip, and they will be able to talk one. And so this chip, that's one way to do the download from the serial. And that's interesting because I thought, well, if I have a serial line, I can put a board on there. But I don't have much tools. Should actually try to install it, and hook it up, and get the switch to run, and says no connection. So that's pretty much the end of the computer. But the board is nice. It has the serial line is and the instructor, it uses the debugging chain for download. So it is a completely different line. Kind of hard to use, but then the Kyle IDE does work. So I was able to download things very okay, so here
This, the kind of architectural you're using have those 2K upper limit.
yes, okay,
So it's a keyboard.
yeah. And my system uses about 10K. So it's a perfect. So this is Taiwanese board. That's the 8-bit subway, and the 30-bit subway. And I think Dave, you must remember this one. And this is the one of the ARM7. This is our ARM7 chip, and we have this board with the LCD display on it. So that was very nice, and that's what I did my one version of my ARM7. So I thought, yeah, I got the ARM7 for code, and all I have to do is just get the tile to compile, pretty much do the same syntax. All identical. So the code is really don't need much modification. But okay, so we have the discovery board, and it uses the STM32F407 PG microcontroller. And it's a tile micro-BT one. And the implementing board. Okay. So, sorry about the title. I think I was taking the my PowerPoint from the 2010 on the SVFIG. The graphic change it really quick. Now the board is to be smaller, not the, it's not, yeah, it's about the same. And the good news is that built-in ST-Link USB device. So this is a different beast than the serial. And the microcontroller there, they got half a megabyte of flash, 192 kilobytes of RAM. So that's really nice. And 8 LEDs and a 3-axis accelerometer and a ton of peripherals. Okay, I think that the 1695 by 50 I tried to order it from SVFIG system, correct? Digital store, and they charged me about $40 for shipping.
Yeah.
So let's just start if you wanted it same day courier.
No, it's just.
Handcuff it to somebody.
Yeah, I think they tried to make up the cost of the $60 from
It was for drone delivery. Yeah.
Yeah.
So, but I think the visit fee charged me about $4. Okay, one thing which is different in this feature and format and format is that it's not ARM instruction set. So in the compiler, the first error message I got is that there's lots of instructions it does not recognize. It says not valid instruction, whole bunch of them. It turns out that you have to set up the processor using fun. I used to say ARM, which is the ARM instructions. And with ARM instruction, it generates lots of them. You have to use done specification. So I was checking done is I kind of like it ARM instruction. Very well. And the thumb instruction set has lots of 16-bit instructions. So, but now the compiler or the assembler will only recognize 32. It's a mix of 32-bit and 16. Which is I don't know, but the reference manual is 17 countries. And I say the example you see is horrible. You just think get through the startup page. That's this good. So at first in the old in the same setup, I just grab the startup file and add on the import as the assembly file. So, but I do have much courage to change the startup file. But I'm looking at the stock file in the it's just too much. So I wrote through all the examples, and I got some really nice stock code. The assembly says you don't need all this startup. All you have to do is implement reset method. And you only need to specify the first 8 bytes in the method. Forget about the implementation. You don't need that. And I don't do anything else. You only have to worry about the first 8 bytes. And then you're on your own. So with that nice discovery, well, I can handle that. And then I still need a serial. I still need a serial. But the board, the chip, has 6 USR antennas. So you can use any of them. But since haven't used 4-screen board, it's using USR 1 port. Stick with that port. But that port is not connected. It's connected. But the keys, you have all the keys. Try how to do the serial. I just use that to move up one port to transmit and take it through. And add into the Arduino Uno board. The Arduino Uno board, if you remove the CPU, the transmit and the emit is still connected to the UART. So you could just connect the transmit, transmit and emit pins to the Arduino Uno board. And then you can use the Arduino function. And that's what I did. So I have this board hooked up to the Arduino, remove the CPU on the Arduino, and then zero on Okay, so this chip is, I think that this is Moore's law going to the extreme. 4 years ago, I did that with Gen 7. I forgot how much memory. But this series, 4.7, has up to 1 megabyte of flash and 192 kilobytes of RAM. And that's 192 kilobytes of RAM. That's nice. Important data. And the clock is one. You can clock it up to 168 megahertz. Okay. But when you boot up, you do nothing. There's an internal oscillator, 16 megahertz, internal oscillator. And this internal oscillator is factory rate tuned to 1% at least. So this internal oscillator is good enough for one. You don't have to do anything. Just assume 60 megahertz and work out the and then the slide doesn't have enough space to get all the nodes. And I think we attached 8 GPIO, 17 timers, 6 UART, ADC, about how many channels, EOC, SPI, and everything. You manage to have it. That's why we got so many code in the spotlight. Okay, some interesting thing about the F2. It's supposed to be a RISC machine, right? It's the advanced RISC machine. But it's the ridiculously complex instruction set given. Okay? That's what 22 is. But very nice thing, since it has lots of memory, lots of props, and we implement that nested implementation. And it actually does, or actually encourages the entry. That's very nice. Depending on the chip, you can have over 140 IOPs spreading out into all these various ports. 7 timers, 6 UART, 2 USB. I think it's nice. It has 2 USB. I will learn USB on this chip. And it has a potent but it only uses certain single precision. I think that I look at it now, I think multiplied by distributed. That's all it has instructions. The instruction set, instruction set, it's a mixture, a combination of firm instructions. I think it's backward compatible. Um, but the assembler kind of doesn't allow you to go back. So it has many different ways to access memory, just like systems. All modification instruction on command has signed and signed, blah, 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 modifications, whole page on modifications. And you don't need two. And it has a very special bit modification. Actually, it has in the middle for I/O to access the I/O or search among the memory. It uses what's called a bit bank. So if here you have 1 megabyte of RAM, and it opens up that 32 megabyte space in another area. And from this 32 megabyte memory, you can access this 1 megabyte memory bits. Any of the bit memory access to 1 bit. So that's very nice. It's very fine in the code. Numbers. For the microvision 521 tool set, the limitation is 32. It's free. You could only go to 33. Only compare. So it has a very nice picture. And it could hook it directly to the SVFIG. And then it supports as instead of the SP microsystem, instead of doing their own IDE, they kind of third party. And I'm not using it. Oh, the shoot. I really want to talk about it. Well, unfortunately, because there was the ARM4, which I did for the Game Boy 2000, and then moved on to APU suite, that's analog. Analog. There, on, and then moved on to C7. Not much you can change. But there's lots of one big problem is 16-bit thumb. So I got about 90 warnings, errors, warnings that these some instructions that need to be word aligned. But because of the 16, some of the instructions are assembled into 16-bit instructions, but they misaligned. We got lots of warnings. That they all warnings that doesn't matter. But then, the program doesn't work because it fails with zero, no field. And if you get to any of this point, so I have to put all the warnings. So when I started, I said, well, all I have to do is first I want to write down all the warnings. So that I'm control. And then I want to send out a message to the USM port. you will use sure that I am handling it. So the first thing I pulled up, first thing is write up what you use, and then send comments. Pull up. Disable all interrupts. And currently, each process are being showing I think one of the options is to copy everything from flash to RAM. The advantage is like making the RAM, I can just regularly extend it, add new words. But in the, if it's in the flash memory, it's kind of hard to but I think I look at one of the implementation skills that actually works the new words were added. Then that might be another way. Okay, so here is the discovery port connected to PC, and you are connected to other terminal to an Arduino chip, an Arduino board, and after using a sample CD board, and then
There you go. Cool.
But I cannot right now. Cannot punch. So in terms of I think the easy way is to add that to change the comma to right. So that's I think the easy way. The hard way is to on boot up, copy everything to the RAM and run it. Another thing about this chip is that it has 3 different boot modes, depending on 2 external pins, boot 0 and boot 1. If normally if all these are low, if boot 1, boot 0, boot 2 are 0, then it boots up into the flat mode. And if you set up the first bit for the first bit, boot 0 up, so you have 0, 1 type, then it boots up to the system type, and that's the boot code. You execute the boot code. And I think if you set the pin to 1, 0, then it will start from RAM something. So when all this, if you have the free memory, then you can do that from the flash, system RAM, and system ROM. Then on this setup. And this setup can be manipulated in software. And one nice thing is that in the memory map, from 0. Memory 0 doesn't have anything. Memory 0, that page is simply mapped to ROM or to flash to RAM or chip. So this way you can manipulate so one way you can write boot up from the RAM, from the flash, and that's because the flash is by default, flash is mapped to memory 0. After you boot up, you can copy the RAM image into the ROM, and then remap the system so that the memory 0 is mapped to SVFIG. And then inside the RAM, depending on the package inside. That's I think that we have to and then you can just add them. If you are running in RAM, you can add the recode. So we have 192 kilobytes. Yeah. And after you're done with computation, you just copy this entire entity. So that's the option that okay, so that's the thing already. These are not like I look at this before. And I'm really proud of this one because you are. It's always hard to get a new art. But now, if I just get a new art, or have to read a new art, and then
You're doing it because of the RS-232 level driver? Or?
No, you don't, that's the point. You don't need the level chip. So from chip to the from this chip to this it's all the roll up fiber. You don't need the level chip.
But the real board provides that level shifting? So
no, Arduino take the signal and go to its USB-C.
Have you seen this? That's USB serial port.
Yeah. It's always.
It's on a board now.
Yes, I know, but it's always another board.
Correct.
And then the
Correct.
driver.
Well, it is also in just a cable.
You
can do the same
yeah.
thing.
At one end, RS-232.
Yeah.
You know what we can do is have an ad hoc talk in the afternoon about that particular aspect of Satan's project here.
Yeah, you could.
And you can be around this afternoon?
Yeah.
Would you mind talking a little bit more about it?
Sure.
So the short shift this morning.
And you guys fast.
All right, let's put that on the whiteboard for this afternoon and head for lunch.
We're gonna stop. Tell them we're stopping.
Okay.
Stop broadcast.
Okay. Thank you very much for joining us on the internet here in Corpus. We're going to be going to lunch now. We may start earlier than scheduled because something interesting may be happening that's of interest not only to us here but also to you out in the world. So we'll welcome you back. We'll send an email hopefully in advance of anything interesting happening, and we'll see you then. Bye now.
We have 2 viewers.
Two